Hello everyone, welcome to Chapter 4, Routing Contents. A router connects one network to another network. The router is responsible for the delivery of packets across different networks. The router uses its routing table to determine the best path to use to forward a packet. If the destination is not on the network, it sends it to the default gateway. Routers are computers, basically. They are also network-capable devices, so they have these components: the CPU, an operating system, and memory and storage. These are the different types of memory that a router can have. Different things are stored inside different types of memory. For example, RAM stores running iOS, running configuration file, IP running, and ARP tables, and the packet buffer. Some of these are volatile. Well, only this one is volatile, and these three are non-volatile, which means that volatile memories are lost when power is lost. As I said previously, routers forward packets to their destinations. There are three main forwarding mechanisms. First one is process switching. It is very slow, rarely used, and very old, so it is not recommended. The second one is fast switching, which is faster than process switching, but it is not the fastest. The best method to use is Cisco Express Forwarding, which is Cisco proprietary, so only Cisco switches support it, Cisco routers support it, and it's the most efficient, the fastest, and also the easiest to implement. Here's an easy way to remember different types of forwarding. Process switching solves a problem by doing math longhand, even if it is the identical problem. Fast switching solves a problem by doing math longhand one time and remembering the answer. And the Cisco Express Forwarding solves every possible problem ahead of time in a spreadsheet. In order to connect devices into a router, they must have these three basic configurations done: an IP address, static, a subnet mask, and a default gateway. It is very important to always document the topology and the addressing table of the network we are building. This is done very easily. Device, interface, IP address, subnet mask, and default gateway. It's also recommended to always configure these three settings inside a router or a switch: the hostname, to secure privileged exec and encrypt passwords, and configure a message of the day.
Switching packets between networks. First, we will see the switching function. That is the process where the router accepts a packet on one interface. This switching is completely different from switching of layer 2. First, when a router receives a packet from one network and needs to go to another one, the router follows these steps. First, the router encapsulates layer 2 frame, header, and exposes layer 3 packet. Examines destination IP address of packet to find the best route. If it finds a path to the destination, the layer 3 packet is encapsulated into a new layer 2 and forwards the frame to exit the interface. In the next frame, we will see how this process is made. How to send a packet. First, PC1 sends a packet to PC2, and the first thing that PC1 must determine is if the destination of IPv4 address is in the same network. By using some AND operations, the PC1 determines if a packet is in the same network. If this is the case, then PC1 don't use the default gateway. But then, if the packet is not in the same network, PC1 refers to the ARP cache in order to search for the MAC address of the packet. If the MAC address is in another network, then the packet goes to the default gateway. For example, we see here that PC1 is searching for the best path to take in order to get to the router. So then, if PC1 sees that the PC2 is in a different network, the thing that PC1 must do is to determine the MAC address of the default gateway, that in this case is FA0/0. So how can PC1 can do that? First, PC1 checks its ARP table that we can see here for IPv4 address and its associated MAC address that it is that. And then, if it doesn't exist the MAC address, the PC1 sends an ARP request, and after that process, the packet can be delivered to the correct interface of the router, that in this case is FA0/0. And then it is the same process with the IP version 6. So after all, the PC1 can deliver the packets to the router 1. Forward to the next hop. In the last step, the router 1 has our packet, but now router 1 must examine MAC address in the interface. When the router 1 sees that it contains the Ethernet field that it is, means that it contains an IPv4 packet, so router 1 encapsulates the Ethernet frame. So here the router 1 sees that it sends the MAC address. Here it sees the destination IP of the packet. And then here the router 1 sees that the destination IPv4 does not match with any of its directed networks. So the router 1 consults its routing table for a network address. Here is the router 1 routing table, and here is the destination network, and here is the next hop IP, that it is the IP address of the router 2. So when the router 1 have the route from his interface FA01, he needs to reboot the packet. So he sees his IRP cache to see the destination MAC address of the router 2, that is the 0B31, and he puts here the destination MAC in the layer 2 data link frame, and then the ARP protocol says that his MAC address is the 0020. So now the router 1 is ready to forward the packet from his interface FA01 to the router 2. Now that the router is in the packet 2, it must race to its destiny. So it is the same process as if the packet was in the router 1. He must search for the MAC address, so router 1 must investigate. Then he sees that it has an internet. He sees that he has an IPv4 of the destiny. He searches in the routing table and it identifies the router 3 that have directed network of the destiny. So router 2 know that he must forward the packet to the router 3. So up to here is almost the same. But now if we see, we have a point-to-point serial connection. So here comes the difference. Here comes the difference. The source MAC address is not needed in this step because there are no MAC address on serial interface. So the router 2 sends the data link destination address to an equivalent to a broadcast. So now the packet got to the router 3, and we must go to our final step, that is to reach the PC2. Now the router he have the packet, so it is the same process that we have the router 1 to identify the router 2 and the router 2 to identify the router 3. So he must investigate his point-to-point link. Now that he have the encapsulate his data link frame, he see that it has an IPv4 direction of the destiny. So he must search through its routing table and search and see that it has a direct connection to the IP address that is 192.168.4.0/24. That is the IP address of the PC2. That means that the packet can send directly to the destination device and does not need to be sent to another router. Because the exit interface is directly connected network, authority must resolve the destination IPv4 address of the packet with the destination MAC address. So he searches in his IRP cache. If the entry is not clear, he must do an IRP request to have the MAC address of the PC2. So when PC2 sends back an IRP reply to the router tree with MAC address that it is the 0B20 and the source MAC address of router tree that is 0C22. Now the router is prepared to send the packet to the PC2, and there is how a package is sent from PC1 to the router 1 and then to the router 2 and then to the router 3. Here is the switching function of a router. Here we see a diagram where it resumes all the steps that we have previously seen. As we see, the packet arrives on the interface. Next, the router searches for the routing table for a match, as we see as the router 1, router 2, and router 3 have done. Then the destination address match the subnet of, and we have here two options: to a directly connected interface or to a remote network. If it is a directly connected interface as the router 3 and PC2, next we only have to check the ARP cache and forward to host on local subnet. And if not, as the router 2 and the router 1, we must encapsulate the frame and forward of the exit interface to the next hop. We can see an example of that with the router 1 when we have to encapsulate the frame again and send it to the router 2. But if it is not neither in a directly connected interface and neither in a remote network, we must see if there is a way of last resort available. A gateway of last resort available is sent when a default route is configured on a router. If there is a default route, the packet is forwarded to the gateway of last resort. So now, if we have this gateway, we encapsulate the frame and forward out the exit interface to the next scoop, as we have done in the remote network. But if it is not a gateway of a last resort available, we must drop the packet and send an ICMP message back to the source IP address. Imagine that in the previous example, we have more than one route. The router must have a method to choose the best path. So in this example, we have PC1 and two possible routes. We must have some protocols in order to the router choose the best path in order to go to the PC2. So the best path is selected by a routing protocol on the value or metric is used to determine the distance to reach a network. What is a metric? A metric is a quantitative value used to measure the distance to a given network. The best path to a network is the path with the lowest metric. For example, we have some protocols like the router information protocol that uses a hop count. It means times that a packet goes to the router 1 and router 3 and then goes to the PC2. We also have the image interior gateway routing protocol that it uses the bandwidth, the delay, the load, and the reliability. Also, we have another protocol that it is not shown in this animation, that it is the open shortest path first, that is a Cisco cost based on cumulative bandwidth from source to destination. And well, in the animation we can see how the path may be different depending on the metric being used. For example, the routing information protocol, we see that it uses a hop count, as I have said, and the image interrogate gateway routing protocol, it uses the bandwidth, the delay, the load, and the reliability. Here we see the hop count another time, and now we will see the bandwidth from PC1 from PC2. Now, what happens if a routing table has the same metric in two paths? For example, in this animation, we have the same metric between router 2 and router 4 and router 2 and router 3. So how can we deal with this scheme? First, when a router has two or more paths to a destination with equal cost matrix, as this example, it uses the both paths equally. It means that it will do something like that. First, they go to the router 1, then to the router 4, and also go from the router 2 to the router 3. So this effect is called load balancing. It means that the router forwards packets using multiple exit interfaces listed in the routing table. But how can this load balancing improve the communication in the network? Well, load balancing can increase the effectiveness and performance of the network because equal cost and load balancing can be configured to use both dynamic routing protocols and also the static routes, as we can see. It is important to note that only the ARGRP supports unequal cost load balancing. Finally, it is important to note that a router can be configured with multiple routing protocols. For example, IEGRP, EGRP, OSPF, IRP, internal BGP, and also the static ones. So the router can have more than one protocols as this one. However, each routing protocol may decide on a different path to reach the destination, based on that routing protocol's metrics, that it is this. Cisco iOS uses what it is known as the administrative distance to determine the routes to install into the IP routing table. Here we have the administrative distance if we have two networks directly connected, the static, the administrative distance of the IGRP summary route, and another administrative distance for another protocols. The administrative distance represents the trustworthiness of the route. The lower administrative distance, whereas an IRGRP have an administrative distance of 90, and the static have an administrative distance of 1, obviously it will choose the static one, because the router also chooses the one with the lowest administrative distance. And in this list we can see how the protocols have been connected with also the administrative distance of each one.
Specifically speaking, a routing table is a file located in the router's RAM used to store information about directly connected routes and remote routes. Directly connected routes represent the networks connected to a configured interface of the router. Remote routes represent networks connected to other routers. The configuration of both will be later discussed. One concept that is important to consider is the next hop association, present in the routing table. Next hop associations, or network associations, tell a router how can a particular destination can be optimally reached. This is done by showing the next hop, or router, that a packet has to be forwarded to in order to get to the final destination. A route can be learned by using several methods. The way how a router adds a new entry in its routing table is known as the route source. The route sources are identified by a letter. The most common codes are the following. L. This code identifies the address assigned to a router's interface. C. It means that a network is directly connected. S. It means that a remote route was manually configured. D. It means that a remote route was dynamically learned using Enhanced Interior Gateway Routing Protocol. O. It means that a remote route was dynamically learned using Open Shortest Path First Protocol. It is important to fully understand the entries in the routing table. First of all, we must take into account that the routing table entry for directly connected networks is simpler than the entries for remote networks. The directly connected route entry contains the following information. The route source. The only source codes available for this type of routes are C and L. The destination network address and the outgoing interface, which is the exit interface to use when forwarding packets. As it was mentioned before, the remote routes contain more information in their entries. The router source, the destination network, and the outgoing interface are also present in remote routes. But, because we're talking about remote routes, the following information has to be taken into account. The administrative distance. That is a concept that was previously discussed. It identifies the trustworthiness of the route source. The metric, which identifies the values assigned to reach the remote network. And the next hop, that identifies the IP address of the next router to forward the packet to. The parameters also include a route timestamp, which identifies how much time has passed since the route was learned. Now it is time to talk about the directly connected routes configuration. In order to add the interface to the IP routing table, we have to apply the following changes. First, the interface must be assigned with a valid IP version 4 or IP version 6 address. Then, the interface must be activated with the no shutdown command. Finally, it has to receive a carrier signal from another device. It can be a host device or another network device. When these routes have been added to the table, static and dynamic routing can be implemented. We can see in this table the main differences between both. A static route, as its name suggests, is manually configured. They define explicit path between two networking devices. They use less bandwidth than dynamic routing protocols, and resource efficiency and security are improved. Also, the administrative distance has a lower value than the dynamic routes. However, it lacks of automatic reconfiguration if the network topology changes, so it is recommended to use it when the inter-network connections are fully understood. On the other hand, dynamic protocols are used by routers to share information about reachability and status of remote networks. Dynamic routes are automatically maintained, and they do not have any issues when the network topology is changed. It uses a special ability called network discovery, which allows it to share information about the networks that it knows about with other routers using the same routing protocol.